Good afternoon, everyone. It is a great honor to introduce Diego Turrini, who's today's joint colloquium speaker. Diego is currently working in Rome. He did his PhD in Padova. During that time, we actually met a long time ago in Cambridge, when I was still a master's student, and Diego told me what it was like to do a PhD, and then decided I wanted to do a PhD. It's actually your fault. So then in 2007, you finished your PhD, went to Rome for your postdoc, and then Diego became a permanent staff member at the National Institute for Astrophysics in Rome in 2015. In 2014, Diego was the first Italian to win the Zeldovic medal from COSPAR in the area of planetary sciences. And in 2017, he had an asteroid named after him for his involvement in the NASA DOME mission. So currently, Diego is a major player in satellite missions exploring the solar system, its asteroids and planets, working with both ESA and NASA. And at the moment, he is a member of the core science team for the NASA-ESA aerial space mission to do spectroscopic surveys of exoplanets. And he's one of the main proponents in Europe for a NASA-ESA mission to Neptune and Uranus, which may fly in the 30s and will hopefully get there by 40. Is that?
That's the plan.
That's the plan. Okay, well, fingers crossed. I'd like to go there. And so today, Diego is going to tell us about Vesta and Jupiter's formation through astrochemistry. Over to you.
Okay. So, given that Diederik tried very hard to build my credibility as a scientist, let's destroy it immediately. So the story that I'm going to tell you today, which involves, as you see, a lot of people from different groups, some of which I was part of, like the NASA DOME team, other I led, like the International Space Science Institute team that studied how we can use Vesta to understand the formation of the solar system. And this started in 2008 as a short work to be presented at the Lunar and Planetary Science Conference. My supervisor at the time actually told me, I have an idea for a quick work, it's just going to be a couple of weeks of work, we're going to be done with it, and we make a very good impression to the DOME team. 10 years later, we published the last bit on this work. It worked well, we just got the timing wrong. So, let's start setting the scene, which is the problem of planetary migration. Some of you in the audience already know much more than me about this. Basically, the classical idea for the first half of what we can call modern planetary science that started more or less at the time of the space exploration of the moon is that planetary formation was an orderly process that took place locally, created very stable planetary system, very well behaved dynamically, with planets in different classes well separated in mass, which, like all nice ideas, proved to be wrong. Because when we started observing extrasolar planets, we saw, here you can, in the distribution in semi-major axis and mass, that first there is a continuum in mass. There is no clear jump between one class and the other, aside for a couple of points. And most importantly, there is a huge population of planetary bodies that orbit very near the star. In this plot, Mercury, which is the innermost planet of the solar system, would be here at 0.3. We have the majority of the planets that we know up today around other stars that are between 3 times and 30 times inward toward the star, the Mercury. This alone is an indication that these planets should have migrated because there is not enough mass in disks to form these planets, especially the ones that are Jovian masses. But exoplanets told us also something else. A lot of the planets that we know have high orbital eccentricities. They are not on circular orbit, like in the solar system. They have eccentricities that are 1 order of magnitude higher. This is an indication that something happened in the system, something that generally should be linked to a chaotic evolution or exchange of angular momentum. And the model that explains this, the basic mechanism, is that of planet-planet scattering. So you have encounters between 2 planets, you have exchange of angular momentum, and you have a change in their orbital elements. This idea was put together to explain the existence of systems with innermost planet very near the star and also planets on very out orbit. So the basic idea is if you form a planetary system after the dispersal of the disk with a separation between the planets that is below a certain critical value that depends on the mass of the planets at the distance, this system can become unstable over a certain time scale. You start having a chaotic phase where there is an exchange of angular momentum, the orbit gets elongated, they cross each other, you can end up with the expulsion of one of the planets, and the other planets significantly changing their orbit. This is the three planets version, there is also a 2-planet version. This mechanism seems to work. We were unsure how many planetary systems would cross this phase of chaotic evolution, until we started getting more statistics on exoplanetary system and the orbital elements. In particular, we found that there are some fingerprints of these chaotic events in the angular momentum of a planetary system. If we take the planets and we divide them by multiplicity, which is the number of planets in each system, so that x-axis is just all the system with 2 planets, 3 planets, 4 planets, 8 planets is the solar system, and the 7-planet case is the TRAPPIST one, very famous exoplanetary system. You can see that there is a decreasing trend in the average eccentricities. This by itself doesn't mean a lot, even if this is done with hundreds of planets, so it is a statistically robust sample. If we do the same thing, checking the angular momentum, and we compute the difference between the angular momentum the system would have if the orbit were coplanar and circular, like we would expect from a stable planetary system forming in an orderly fashion, and we compute the difference in angular momentum, we find again a decreasing trend. This means that there is a deficit in angular momentum that increases for lower number of planets. What does it mean? This is a very complicated way to say this. If we see a system with a large number of planets today, this system, if these results are correct, likely was stable throughout its life. And we'll have an orbit that are mostly circular and coplanar. The more we move toward a smaller number of planets, the wider the range of orbital configuration we'll see, because together with the stable system, we will find also contaminants that were systems that formed with more planets, lost planets, and today we see them as systems with less planets, but with this heritage from the chaotic phase, which is per se an indication that chaos can play a role in the evolution of a lot of planetary systems, if we see them statistically. But now, thanks to ALMA, we see the features of exoplanets forming, well, giant planets, exoplanets, forming in circumstellar disk. And in at least one case, we could see a giant planet that is already on a hot Jupiter orbit, so very near the star, a fraction of astronomical unit, when the disk is still there, which is an indication that this system likely underwent, this planet arrived there because of migration for exchanging of angular momentum with the disk. So we have 2 processes at play, and when we see an extrasolar planetary system, we don't know which one of them scattered them. We need to find tools to deconvolve this problem. These ideas that came from the study of disk and extrasolar planets also brought new ideas to the solar system, because if stable systems are not necessarily the norm, if there is evidence that systems can undergo a large scale instability and undergo chaotic phase of evolution, why couldn't the solar system have gone through the same process? This brought to what is formally known as the NIS model, from the name of the city where the scientists were when they devised it, which is the animation on the right, which proposed that somewhere between 500 million years and 1 billion years after the beginning of the solar system, the giant planets, which were much more nearby each other, went unstable, and this destabilized the trans-Neptunian region, which are the green particles in the animation, and formed what we see today as the trans-Neptunian region with an hot population of scattered bodies, and more importantly, deliver water to the Earth in a systematic way, and could produce the habitable environment that we see today, which would fit nicely with the dating of the appearance of the first trace of life on the Earth. This brought even more wild ideas, like the one on the left, where it is thought that the giant planet could have migrated much more than originally thought, with Jupiter arriving to the orbit of Mars and then being pulled out by Saturn, and this way shaping the formation of the terrestrial planet in the inner solar system. What is the problem with these ideas? The main problem is that also the classical models for the formation of the solar system in an orderly fashion can produce something similar to the solar system we see today. So, from orbital data alone, we don't have enough information to deconvolve the history of the very solar system where we live in, let alone the extrasolar planets. So we need to find some trace or some tracer of what happened that can allow us to compare the different models and identify which one are the realistic one. So now let's put this problem with migration and understanding how it shaped the history of the planetary system and the solar system aside, and let's introduce the first actor of the story, which is Asteroid Vesta. So we were talking about the fact that we observe planets forming in circumstellar disk, and we know that giant planets should form in circumstellar disk because they need to capture the gas from the nebular environment. The moment the disk disperses, there is no hydrogen and helium for the giant planet to accrete most of its mass. But we don't know anything. We cannot study the solar nebula or the circumsolar disk directly because it is long gone. We know that should have lived up to 10 million years, because that's what the statistics on other circumstellar disks tell us. We have circumstantial evidence that the life of the solar system should have been between 3 and 6 million years. So it should have been some sort of average lifetime for a circumstellar disk. Where do we get this evidence from? We get this evidence from meteorites. Why they cannot tell us directly about the life of the solar nebula, or they can tell us when the planetary formation process starts, and they can give us a lot of details of the steps of this planetary formation process. So we get a very detailed view of the time scale. For example, in this plot, the gray stone that you see indicated by an arrow is currently holding the record as the oldest solid in the solar system, dating back to 4,568,000,000 years ago. And this set the zero time for the beginning of planetary formation in the inner outer regions of where the material was evaporated and recondensed at a later time. So, in a nutshell, what we do is we use meteorites as cosmic fossils to try to get a glimpse of what was happening 4.5 billion years ago in the solar system. We do this thanks to a series of radiometric clocks based on the decay of radioactive nuclei. If some of you is familiar with the carbon dating for organic material, the basic principle is the same. There are a lot of clocks that trace different things. I'm not familiar with all of them. The most important one for our purpose is the fact that some of them have elements that remain with the rocks, and others have decay products that move with the metal toward the core of the planet when they undergo geophysical evolution. So from the separation and the ratio between these elements in the crust, we can date when the crust crystallized and no movement was possible. And this gives us an idea of when the planetary body was evolving. At the beginning, the data were telling us two things. There was one family of bodies that were composed of material that never underwent this kind of processing. It was never heated up, it never melted, and it is pristine. It is a pristine example of the material that was around in the form of planetesimal in the solar system. And these were older. And then there were material that instead came from bodies that underwent this geophysical evolution, formed differentiated bodies like the Earth, so a crust of light rocky material, a mantle of intermediate material, and then the core made of metals. And this formed later, and the idea was, oh, wonderful, this is like the time scale of growth. The first bodies are the ones that remain small, below around 20 kilometers, so never accumulated heat and differentiated. The others are those that grow bigger and could differentiate. Nice idea, wrong. Because there is this family of metal meteorites that actually predate or are contemporary to the primordial one and tell us that in reality planetesimals were forming on a time scale that is getting shorter and shorter by every year. At the moment is around 10 to the 5 years based on meteoritic evidence. So very fast. We started forming the first solid, and 100,000 years later we already had things that were 20, 100, 200 kilometers in size around, or even bigger. One of these bodies holds a special place. It is associated to a family of 3 different kinds of meteorites. For the moment, I will introduce 2 of them. They are the Eucrites and the Diogenites. These are volcanic rocks that in the 70s someone thought of a nice idea. Let's take these meteorites we do the infrared spectra in laboratory, we go observe the asteroids, we do the infrared spectra, we find the one they match, and we found the source region of the meteorites. Brilliant idea. So they applied it to one of the brightest asteroids in the asteroid belt, Asteroid Vesta. And they got a very good match, which brought to think that Vesta was the source of these meteorites. It was a wonderful technique that only worked the first time they applied it. It never worked again, to such a good degree, in reality. It works, but not one-to-one. So, thanks to these meteorites, we know that Vesta already completed its geophysical evolution and formed a stratified structure 3 million years after the oldest solid formed. And if you believe geochemists and geophysicists, this means that it Okay, so that is a nice idea. If Vesta was there, it could preserve some features that are a relic of this time. But is Vesta truly the parent body of these meteorites? So can we trust its dating? That's why NASA sent the Dawn mission that was launched in 2005 to explore this asteroid Vesta and another asteroid series. It is the first mission that actually went in orbit around 2 different planetary bodies. One of its main goals was to test this idea that Vesta was the progenitors of these meteorites. So they had a suite of instruments that could measure spectroscopically and compositionally through gamma ray and neutron spectroscopy the composition of the surface of Vesta. And what they found is that both in the spectra, the surface of Vesta overlap with both the Diogenite and Eucrites, which are the yellow and violet ellipses, but mainly with the 3rd component of the family, the Howardites. What are the Howardites? The Howardites are just a mix, 2-to-1, of Eucrites and Diogenites that have been broken by impact, then recementified by impact. They are basically the space equivalent of sedimentary rocks. Instead of having wind erosion and compactification by water or pressure, you have impacts playing the game, or recreating rock from fragments. Also with gamma ray and neutron spectroscopy, we found that the iron, oxygen, and it is missing on the vertical axis, but that's the silicate-iron ratio, are identical to that of Howardites. So, compositionally, the surface of Vesta is just a huge mixture of these 3 kinds of meteorites. Wonderful! That means that Vesta is really linked to these meteorites, and we can get an idea of the internal structure of Vesta. Why? Because the primordial meteorites I was telling you about at the beginning, the one that never underwent geophysical evolution, if we study their composition, we see they have what we can call a chondritic composition if you are a meteoriticist or a geophysicist, or a solar composition if you are a stellar astronomer. Basically, the ratio between the different elements is the same as the sun. The absolute value change, but the ratio is the same. So it is the product of a condensation sequence. So, if the abundance are the one in the sun, and we know how much elements are in the crust thanks to these meteorites, by difference, we know how much material is inside, which allows us to tell that Vesta should have an iron core of around 110 kilometers in radius. Then there is a mantle of this mineral asborgite, which is olivine, which is the yellow crystal inside the top picture of a meteorite, which is weird because on Earth olivine appear mainly green, hence the name, and in space it is yellow. And then we have the crust, and the crust is reasonably thin, is 30 to 40 kilometers in thickness. So that's the information that we get from the meteorites. We sample the surface and we get a glimpse of the internal structure. But Vesta told us also something else. The surface of Vesta is not clean, it's dirty. Dirty by a dark contaminant that looks like the pristine meteorites that I was telling you about, and contain traces of water that could be picked from orbit, both spectroscopically and with gamma-ray neutron spectroscopy. Thanks to this information and the fact that Dawn could actually put an upper limit and quantify how much water is in the crust of Vesta, we could do the first studies of impact contamination, quantitative studies, to see if this material could be delivered by impacts. So material falls on the surface, deliver water, like the meteorites on the Earth, just at a higher scale. And we found an extremely good agreement. So the process, for the first time, was studied in space, in a range of impact velocity which is similar to the one we have during planetary formation. We also got another interesting information, which is the fact that howardites are a mix of Eucrites and Diogenites, 2-to-1. But if you look at the amount of metals that are inside, they are overabundant. If you see the orange line, below you have the pristine material that you combine to form the howardites. Above you have the howardites, the bulk of the howardites. They have more metal. And given that these materials are produced by impacts, could it be that impacts deliver these extra metals that in Vesta are in the core but in pristine meteorites are still mixed? And the answer is yes. The average value of the howardites is 300 parts per million. And actually, if you do the computation of the contamination, you get 300 parts per million, which is weird. As a theoretician, I can say it is weird to find a one-to-one agreement, which could be a coincidence, but at the moment we want to believe it's right. So, thanks to Dawn, we got confirmed that Vesta is our oldest witness of the life of the solar system. We could study the role of impact processes in bringing material between different bodies. So why do we care about this? Because there is a link between Vesta's evolution and Jupiter formation, and more generally between the formation of giant planets. So from the study of meteorites, we got 3 facts about Vesta. First, we know that the crust is composed by these 3 kinds of meteorites, and the crust is still there today because we observe it. The second is, thanks to the Dawn mission, which turned on the interest in Vesta again and prompted a further in-depth study of meteorites, we discovered that Vesta is a dry, volatile poor body that shouldn't have any water, but in reality there are small traces of water. And if you are a geochemist, which I'm not, so I believe them, this tells you that there is an upper limit to the amount of water that was around at the time. They also tell us that the other elements, diogenites, contain an enrichment in metals, or high siderophile elements, which should be elements that migrate with the iron in the core. But wait a second. Water, which is traced by apatites, which are a mineral that form only in the presence of water, and siderophile elements, or metals, are those that we saw on the surface of Vesta brought by impact. These were not delivered mixed mechanically like in our dyes. These were delivered when the body was still molten, so in the first few million years of the life of the solar system. Therefore, could it be that they were delivered by impacts? Maybe there was some material that was already original from Vesta, but surely impact could deliver more. So, thanks to the work of clever geochemists and mineralogists, we can transform these 3 facts into quantitative constraints. First, because the crust is 30 to 40 kilometers thick, we know that Vesta should not have lost during its life more than 15 to 21% of its mass. VT% is weight percent, is mass percentage, is a geochemist unit of measure. Apparently I picked up the habit. The second is water should not exceed 0.03 mass percent, which seems a low number, but the Earth has a water presence that is about a factor of 2 higher. So it's not so low in reality. West is not so dry as we thought. And finally, in order to explain the metals and not have too many metals around and produce a global signature, impact should not deliver to Vesta more than 1 to 2% of its mass. So we have this 3 quantitative constraint. How do we link this to Jupiter? And that's the piece of work that we started doing in 2008, and we should have been supposed to be a very quick job. basically, most models have planetary migration, shifting material, like you can see in the last two plots, through sweeping resonances. So the material gets trapped in mid-motion resonances with the planet, or gets scattered away and move with the planet inward. So you bring material from cometary material nearby the inner solar system. But what we found is that you don't need migration to do this. This happens also if you don't have migration, just because of the mass growth of Jupiter. And the principle is actually very simple. You have a disk with a lot of small planetesimals that are in thermal equilibrium, like molecules in the air. They bump into each other, but they get in a state where statistically they remain in the same global state. Then you suddenly introduce a giant planet, which changes the equilibrium. Particle becomes unstable and gets scattered. The particle enter the resonance, which are those pillars that you see. And why does this interesting for Vesta? If you look at this triangular shape that I draw, bodies that end up inside the triangular shape can cross the orbit of Vesta, so they will produce impacts on Vesta. Impacts will deliver material. And this will happen independently of what the giant planet do, even if it forms where it is today or it migrates. But the structure of the dynamical structure of the body, so the impact velocities, will change, and also the material. Here I draw with 3 different colors, 3 different sample population. Red are the very dry rocky material, so just rock and metal. Light blue is cometary material, everything that forms beyond the snow line that contain large amounts of water in the form of water ice. And the grayish population, intermediate population, is those pristine meteorites that are mainly made of rock but contain a bit of amount of water. And if you look in the triangular region, you see that the proportion of the 3 different families changes between one scenario and the other. Here we have the first one is the case of Jupiter not migrating, so in situ formation. Then we have a quarter alpha 1 astronomical unit, which when we did the simulation in 2011 and 2010 and 9, it was already a wild guess. Nowadays we have scenarios that have Jupiter starting forming at 20 astronomical unit. So we need to expand. But for the purpose of what we wanted to do, this was enough. So we got dynamical simulation that tell us how many planetesimals from the different compositional region can impact on Vesta. Then we run impact studies. So for the different impact simulations, for the different impact conditions in terms of velocity, how much material of the projectile survives and is not vaporized by the impact, so we can deliver that water or metals that we see mixed in the material pristine from Vesta. So we run different simulations from pure water ice comets, rocky material, mixture. And when you do impact simulation, it's not just a matter of velocity, it's also a matter of size. If you think about it, it's obvious. If you drive your car and you have a fast impact against a mosquito, you don't get any problem with your car. If you have even a slow impact against a wall, and then you need to change at least your lights or something. So it's much more expensive and destructive. Same with impacts between planetary bodies. And we don't know what was the size of the initial planetary bodies. We have different models that can produce very initial large planetesimals that are 100 kilometers in size, like in the violet line there. Other models that predict planetesimal formed with a few kilometers in size. Models that predict a very fast collisional evolution where you get most mass in very large body and a large population of very small bodies. And models where you have the same collisional evolution producing a large population and intermediate sized bodies from 10 kilometers to 100 kilometers. That changes a lot because it gives you a continuum spectrum of possible impact condition. So I know that I'm putting together a lot of different things, which is one of the reasons why it took us 10 years for the initial idea to arrive to this point. So here's a wrap-up of the basic idea. So Jupiter forms and throws things in the asteroid belt. These can be composed of different elements. Every projectile we can trace to a different composition. we do have the recipe for making the projectiles, and we do have the recipe for making the final Vesta, because we have these three constraints I was telling you about that we need to fulfill. So we can do our mixture, and we can see if it matches the expectation. So this process doesn't work on a yes or no basis. It was more like a Sherlock Holmes approach. You can remove all the implausible scenarios, but it cannot tell you among the scenarios that work which one is the correct one. We will need to find something else. But it's already a step ahead. And it actually worked much better than we thought. Even if we were considering very small migration region was small, when we put all the ingredients together, we removed 3 out of 4 of the scenario we're considering. So for example, an in situ formation, the classical idea, brings too much water to Vesta. So it doesn't work. We should see a global signature, because if you remember, I told you, Vesta has an upper limit to water that is just half of what we see on the Earth, but I think we would agree with me that on the Earth we have global signatures of water, just in the weather aside. On Vesta we don't have this, so scratch this scenario. If we have larger migration, what we get is that you get either too much water or too much metals, depending on the amount of migration, or you can get both, all of them, including too much material stripped from the crust. So that doesn't seem to work. And it left only a quarter of astronomical unit of migration that seems to work like charm. Do you have to believe these numbers? Not necessarily, because we were mixing together a lot of physics, impact physics, dynamical evolution, mineralogical constraint. So we need to cut out something from the simulation, otherwise we would still be here. We made some simplifying assumptions, so some of the numbers will need to evolve in time. Some of these scenarios maybe will be likely, because for example, if you have a larger migration, there is another effect that you don't have here. If you have a small migration, you just excite the planetesimal and the disk. If you have a large-scale migration, you become more efficient, especially if the migration is fast, in throwing away material. So you also have depletion. So if depletion wins over excitation, the scenario can still deliver little material to Vesta. If excitation wins over depletion, you don't get a scenario compatible. So we need to test all the scenarios. But the method seems to be working. And we got another nice surprise. It doesn't just trace migration, but also is sensitive to the size distribution of the planetesimals. So these are the individual results we obtain for these 4 scenarios. The first one is the mass loss, water accretion, metal accretion. What you need to know about these plots is below the red line is good. Within the red line, the red bar, it's okay-ish. Above the red line, scrap it. If you put the 3 together, you get the previous slide. What we saw is that the global pattern is identical for all the different typical size of planetesimals. So impactors of 1 to 2 kilometers in size, to 5 to 10, 10 to 20, or 100 to 200, which trace the different formation condition and evolution speed, how quickly they grind it down because of collision. But in some cases, like here, we have some scenarios that works better for specific kind of planetesimal than for others. Or like here, where you reject those that form in turbulent nebular environment, and you preserve the one that form in a disk where there was very low turbulence. Again, do you have to believe one-to-one this number? No, because we made some simplified assumptions. Our goal was to validate the method, not finding the answer immediately. Also because there is a much larger number of scenarios to test, and it will take much more resources than we have for the moment. Yet, it seems that, thanks to the composition of Vesta, we can trace how much Jupiter migrate, and we can test what was the characteristic size of the body that were around at the time. Which in itself, it's a very precious kind of information, because it's another way to sample directly a phase that got lost from us 4.5 billion years ago. Now, if you read the abstract, I also promised that for all of those of you that don't work on the solar system, I would put something that also deal with other systems. So let's move beyond the solar system. Can we use the same principle to study what is happening in circumstellar disks. Well, clearly we cannot go and sample the transfer of material and the enrichment in water and metals, because we cannot sample directly the population of planetesimals there, except under very special conditions. But we can sample the effect of the impacts in removing material from the bodies, because the material that is removed from the bodies will be in part dust. Dust will be reinjected in the disk. So in principle, we have a contamination in disk by dust. If you are familiar with the field of study of debris disk, these are the equivalent of our asteroid belt around the star, but much more massive. So you have a family of exoasteroids or exocomets that impacting produce dust, and this dust we can see with telescopes also from the solar system. We were wondering, when can we have the same process in disks and have an injection of dust in this disk? We tried with a case study based on this specific system, HD 163296. This is a 5-year, million-year-old system, so much older than what we are, with the age of our solar system when it was finishing the life of the circumsolar disk. It contains at least 3 planets, because at the beginning of the year a 4th planet was suggested. Initially the idea was to have something between the mass of Neptune and Saturn. Now the mass has been revised upward, and they can go up to the mass of Jupiter. So we have 3 planets, a circumstellar disk, and thanks to our observation we know how much dust is there. So what we did is simulate the formation of these planets, without migration in this case, and see what is the dynamical excitation that we see, that we should expect in the planetesimal of the disk. For those of you that are not used to working with orbital elements, so semi-major axis, the distance from the star, eccentricity is how elongated is the orbit. If you want an analog, you can think of it as a dynamical temperature. The higher the value, the higher the dynamical temperature, the more the body can move across the system. The colder it is, the more local it stays. And what you can see is that the moment you form the giant planets, immediately you create this huge population of excited planetesimal, these exocomets if you want, that will cross wide ranges, so they will impact with each other. And what we get at the end of our simulation at 5 million years is this state. The two I forgot to say why I was showing 2. This is the plot, the case with the minimum masses estimated up to now, and this is the one with the most up-to-date values. So alpha Jupiter mass for the outermost 2, and the mass of Saturn for the inner one. And this process works in all scenarios, for all the values of mass that have been reported. But the intensity change. So in principle, we can also try to see if there is a link between the dust produced and the dynamical excitation, so use it as a probe for the masses, which is not necessarily a novel technique. They already do it with the perturbation on the dust and the gas, but here we have another population of dust that can produce additional information. So this is a possible, plausible state of this system now, in terms of dynamical temperatures and the inclination produced. So you also have bodies that are ejected from the plane of the disk and are on very inclined orbit. What is the end result? That impact velocity go from this yellow region that was the initial range of impact velocity, that, given that the scale is not very readable, was around a few tens to 100 meters per second to 1, 2, 3 kilometers per second. So we have 10 times higher impact velocities, which means 30 to 150 times more dust production per impact. So this process can be very, very important in playing in reshaping the dust population. So we still need to finish the quantitative computation. So for the moment, I'm not giving you, I cannot give you hard proof of whether we can actually see this process or not, but we have a very interesting finding. This is the reconstructed dust to gas, gas to dust ratio for the disk, the black line, while the red one is what you would expect from the dynamical perturbation of the planets. The only thing you need to know about this plot is basically, in this region, inside the innermost planet, you should have very little dust, so a very high gas-to-dust ratio, because the planets act as a barrier for the dust outside to migrate inward. That means that the dust that was here moves with the gas inward. The dust that was outside doesn't arrive efficiently here, so you lose dust, but you don't replenish it. Instead, they found that there is a lot more dust. You don't actually see this depletion. The curve is smooth. That region coincides both in position and size with the region where we have the highest impact velocities. So the region where we have the highest dust production. So again, it is a circumstantial evidence. I'm not going to lie and tell you this is hard proof, but it is the encouraging finding that is convincing us to continue doing also the nasty part of doing all the numerical computation and try to explain one-to-one this, if we can. So it seems that if you need to take home something from this talk, we cannot study planetary formation just by studying circumstellar disks, exoplanets, or the solar system. We need to put all the three together because every one of them gives us a different piece of the puzzle. With this, we can see directly the initial phases, but only for the most massive objects. With the exoplanet, we get a statistic of the final outcome, while with the solar system, we get very fine-scale structure details, thanks to meteorites and planetary samples, but only about one case. So we need all of three of them. Dynamics is not enough to find a good match. Finding a dynamical good match to the current situation is not enough to tell this scenario is correct. You need the compositional or astrochemical information in order to draw the complete picture. And never trust someone telling you that this is going to be a very quick job, we're going to be done in a couple of weeks, and then publish an easy paper. It never works like that. Thank you.
Steal your microphone briefly. Apologies. Sorry, Diego. Thank you very much for a wonderful talk, and apologies for the sound problem earlier. Somebody also told me that I accidentally said you got an asteroid named after you due to your involvement in the NASA DOME mission. I don't know if I said that. I guess we recorded it so we could check, but I obviously meant Dawn. So, questions, please. Andrew, shall we do it such, given that we now only have one microphone, that you shout and you repeat the question before you answer it? Would that be all right?
Okay.
Yeah? Thank you.
So in your previous slide, you showed enhanced plastic gas ratios inside here. So what's the effect of that on the estimates? Because often those intensities are used to estimate the mass of the planet. So what's the effect of that on the estimates for the planet mass?
That's a $1 million question, which is one of the reasons why the people in the circumstellar disk community, yes. So right. Sorry, I got enthusiastic. So the question was, if we may estimate the mass of the planets, especially the smaller one, from the dust distribution around their effect on the dust distribution, if we don't have this fit between the expectation and rest, how robust is the estimation of the mass, and how this effect can, of the production of new dust make us get it wrong, the mass of the innermost planet, or also the other planets. And that's actually a very good question. That's one basically it's going to be a feedback process. We are trying to estimate how much dust is produced to see if this process is negligible. Like you need around 50 Earth masses of dust to explain the lack of the gap, and you need to produce it locally. If we can produce these 50 Earth masses there, good. Then we can use also these to get a better fit on the mass on the planet, and we can correct the model. If the process, for example, produce 5 Earth masses of dust, because the time scale is very short, a few million years, okay, scrap it, there is something wrong elsewhere in the model. But if we're right, then they need to re-estimate the mass of the planets. That's why, independently from our work in general in the circumstellar disk community, thanks to ALMA data, now they are trying different methods to estimate the mass of the planets. For the most massive, for example, you can use also the local perturbation in the shear motion of the gas, and not only the width of the gap, to estimate the mass of the planet. That doesn't work for the smaller ones, so that's why if we can find a correlation, that would be very important for the smaller ones, because the smaller ones only impact the dust, not the gas. Hopefully we will have an answer by the next astronomical talk I do in Heidelberg. Yes.
Yes, thank you. Very interesting talk. I was wondering, in your model for the you link Vesta to Jupiter's formation, and especially Jupiter's migration. I was wondering how much does it matter for your initial planetesimal distribution? So, if that's it, because in all these simulations, also in these ones, you basically have a full disk full of planetesimals. But if your planetesimals first, let's say, form only in a small concentric, small region, how much would that actually impact your result?
That's basically the main reason why I pointed out that our goal was to validate the method, and the paper that came out this year clearly states that we are publishing a method. It needs to be tested one scenario by the other. It will impact because depending on the interaction between this region and Vesta, and how distant is this region from Vesta, it will change the flux. So we can get models in which we can have a large migration of Jupiter, but the excited planetesimal don't arrive to Vesta. It is now that the method is validated and is out, it is general, so everybody can use it to test it. We also gave the values for the impact from the impact simulation. So you just need to put inside the mass of your impactor body, get the velocity, you get how much material survive, how much material you remove, and everybody can do the computation because all the equations are there. For example, we were talking last year with Sean Raymond when we had the meeting in Lund. That was also this crazy idea that for some reason there could be gap in the inner region that would explain, for example, why Mars didn't grow beyond a certain point. In that case, some of the components of the flux can change. Our goal is to try now, one scenario at a time, test it and see what is happening. But it must be done on a case-by-case basis, having all the physical, meaningful ingredients.
You talk a lot about the migration of the big planets, but maybe I missed it. But how about migration of Vesta? Why should it have been there all the time?
It shouldn't. The question is, implicit in this model, it is assumed that Vesta is more or less where it was at the beginning of its life, which is a strong assumption, in the sense, but not irrealistic, in the sense that Vesta is in the size region, in terms of how big it is, for which gas drag doesn't have a major effect in terms of migration. So the interaction with the gas is limited only to keep the orbit circular and coplanar, so smoothing down the excess eccentricity and inclination. So we don't expect the gas to have a major effect on Vesta. The evolution of the inner solar system, where we have also body the size of the moons and Mars, instead will play a role. But from other studies, this shift in position that should not exceed half an astronomical unit. So Vesta now is at 2.3 astronomical unit, so it could have been at 1.8 or 2.8. Roughly. So actually we test what happens if Vesta is outward, and we find that it doesn't work. It works basically if Vesta was out. Let me take the plot. It's going to be easier. Okay. Okay. Too much enthusiasm. Okay. So. This is Vesta at its present position, assume the original one. We tried putting it here, for example, which is still the rocky region, but is a bit outward. And we found that basically no scenario is compatible, because it would be basically inside this and this excited region. And in all scenarios, they would fall inside the triangular peak region. So basically, the flux of impacts on Vesta would be much higher, and it would receive too much water and too many metallic elements to be consistent with what we see now. So we are reasonably sure that it was not in this, outside this 2.5 astronomical unit boundary. It could have been here. There are scenarios in which Vesta formed inward and was scattered where it was now. It is a possibility that we actually discuss in the paper. It's one of those scenarios that we need to test. We needed to start from some place. So we couldn't cover all the range of impact conditions. But now that we know that it works, we could shift. If we are unlucky, if we are very unlucky, we can find that putting Vesta here protects us from all this mess. In which case, we probably cannot say a lot. But one step at a time.
Chair, question directly to this problem. So you showed the effect of different migration of Jupiter, but how much would it change? How much would it affect if you form Vesta earlier, later? So if you vary the time of formation and the time you put in the Jupiter, did you do that?
Okay, the question is how much these results are influenced by the formation time of Vesta and Jupiter relative to each other. And that's actually a bloody good question. So, but we discussed this in the paper. Right? We've been honest. I want to emphasize we've been honest. The timing of Vesta formation is reasonably well constrained, both by thermal evolution models, some of which were done here in Heidelberg, also meteoritics data to the first 1.5 million year. You cannot form Vesta in more than 1.5 million year because you don't have enough radioactive elements to warm it up and melt it otherwise. So, and this is consistent with the meteoritic data. So Vesta formation time could be revised downward, so be faster than what we have assumed. What can change is when it begins melting. Because in order to have this effect, that material that is delivered to the magma and is incorporated into the meteorites that we see today, Vesta should be already molten by the time the giant planets form. Otherwise, everything goes in the core and it gets molten all together. But we also have indication from the meteoritic data that the melting was reasonably quick. And this 3 million year age is when the first element, the first part of the crust, the oldest part of the crust, started to solidify. There was always something that was solid and part that was molten. It was a dynamical equilibrium. So some material was solid and and then remelt. Some material was molten and solidified to remelt later until it cooled down and it started to completely solidify. And that started, we can trace the solidification from 3 million years after the oldest solid onward. But before that, it was molten. So for Vesta, we are reasonably sure. The timing is correct. For the giant planets, we are not so sure, because there are some recent work that suggests that the giant planet could have started forming already in 1 million years. Then they stopped at between 30 and 50 Earth masses for 1 or 2 million years. And then they started growing again, which you can explain if when they are accreting the gas, they accrete also a lot of solids that warm up the envelope. They can contrast the gas accretion run away and slow it down. It's a possibility. But, and we have, as I said, from Circumstellar, this is the evidence that at least in one case, giant planets already appeared in 1 million years. So, giant planet could have formed very, very much near the time Vesta melted. Not much earlier. There are new works from some of the meteoritical community, people in the meteoritical community that says that, okay, not those meteoritic data from which it is inferred that Jupiter formed in 1 million years, they are not necessarily correct or interpreted correctly, so I don't know. But unless Jupiter formed extremely quickly, so by 1 million years it was already completely done, with its final mass, we don't expect this whole process and scenario to be challenged, because it seems that Vesta is very friendly for us and did everything very fast and furious. If it is not, well, we have Saturn that should have formed later than Jupiter, and Uranus and Neptune even later, and they also migrate and contribute to this. So if we are very unlucky, we can test with the other giant planets. It is something that only time will tell us when we have better data and we consolidate the idea. But at the moment, the prospect is reasonably positive, that we don't have this timing problem.
Any questions? I have one, if I may. Shall I? Yeah. Thank you, Jacob. So you remarked very correctly at the end that the way forward is to basically combine exoplanetary studies, circumstellar disks, and studies of the solar system. And you've done this amazing work on Vesta, which I think is extremely powerful. To what extent could you look at those same constraints and say, like, okay, Jupiter can only have migrated by about this much, and look at other inner bodies of the solar system? And I presume that the presence of atmospheres would complicate things, but maybe things like the Moon or Mercury, could you place similar constraints and come up with a holistic picture?
Okay, for the Moon and the Earth, no, because the Moon and the Earth formed later. So they appear around 30 to 50 million years later, based on the dating we have. So they are not a big part. Some of the idea, reality, which tells a lot about how thoroughful as a PhD student and a postdoc I was, were already in place for the Moon. So this idea of studying the contamination of the surface for the Moon was, for example, something that is already studied. Also for Mars, there is, for example, the evidence that Mars crust has more metals than it should have, and this should have been brought by impacts, which would have made my life easier if I had known this before I started all this 10 years ago in a quick job. But any planet that was around at the time would have undergone the same process. The problem is that we don't have samples to do this fine-scale study. We have meteorites from Mars, but Mars had a longer geophysical evolution that could have cancelled this. So this is a bit tricky. But something interesting that we are considering studying is how this transport process could have influenced the primordial atmosphere of Mars, because it could have been a way to systematically deliver water to the atmosphere of Mars. For Mercury, it could be interesting, because thanks to the MESSENGER mission, we know that Mercury has a high abundance of sodium in its crust. And why it is interesting? Because sodium is a reasonably volatile element. At just 700 Kelvin, it volatilizes from the rocks and gets lost. And at the temperature that was there at the time when Mercury should have formed, if it formed for material in situ, the temperatures were higher, a factor of 2 higher. So there should not be sodium. And instead, according to the MESSENGER mission, the sodium in the rock of Mercury is twice as much as that of the Earth, which formed in a much colder place and should have higher sodium. Is higher than the one of Mars, which was even farther away. So there should have been some mechanism that brought volatile materials to Mercury when it was forming. Could it be this primordial process? Could it be just simple the gas drag of elements, so the smaller planetesimal being swept together with the gas and migrating? That is a million-dollar question, but it's actually one of the things that we want to study with the now finally launched Bepi Colombo mission. It's basically part of the science case I'm working on for the mission.
Wonderful. Thank you so much again, Diego.
And just a small disclaimer, if you listen to all the presentation and you feel that I left out something that was important or I overly simplified anything, you're probably right, but as you could have noticed, I had to squeeze a lot of different interdisciplinary subjects in just one presentation, so I had to make cuts. Feel free to come and complain if I cut out your favorite part.